Hi everyone, this is coming to you from Education for All. Today we are going to look at partial fraction decomposition. Partial fraction decomposition. We all know what a fraction is. A fraction is part of a whole. A fraction, you know what fraction numbers are. It's part of a whole. If you have like 1/2, this is a fraction, proper fraction. If you have like 3/5, it's another proper fraction. Have like 6/7, these are all fractions. Because it's part of a whole. You have a whole thing, and then you keep dividing it into various segments. So you got a fraction of that whole. But what are partial fractions? And in fact, why do we need to study them? And what are they? Partial fraction decomposition provides algorithms for various computations. They provide algorithm for various computations with rational functions. Because of that reason, we need to study them. They are very important in various fields of science, mathematics, engineering, and other areas. So why are they important? They are important because they can be used in the Taylor, T-A-Y-L-O-R, Taylor series expansion. Partial decomposition, partial fractions. They can be used in Taylor series expansion. And you know what Taylor series expansion is? Taylor series expansion enables us to approximate a function using its derivative at a particular point. It allows us to approximate a function by using its derivative at a particular point of the function. Very important Taylor series. 2, I'll just name maybe 2 or 3. Partial fractions are also used in the inverse Laplace transform. Inverse, this is R, Laplace transform. This again is very important, Laplace transform. You know what Laplace transform is? Laplace transform, it allows us to transform an integral problem in calculus, integration, into an algebraic problem which can easily be solved when you try to transform a problem, an integration problem, integration in calculus, into a simple algebraic form. It makes the problem to be simple, it can easily be solved. But then what the inverse here does is it reverses back that algebraic problem into an integral problem. This is very, very important in calculus. This Laplace transform, Laplace inverse Laplace transform. It makes a very difficult problem to be solved, like partial differential, like differential equations. Differential equations. Let me just see differential equations. These differential equations can be is integration, you know. They can be transformed into algebra after using some algebraic manipulations. Then you can use partial fractions to convert this algebraic function back into integral function. Then you can easily get your answer. This is where inverse Laplace transform is used. And then thirdly, they can also be used in integration. It's also useful in integral calculus. Partial fractions can also be used in integral calculus. Some functions can easily be solved using partial fraction decomposition. So then, what are these partial fractions? How do they look like? In algebra, if you have, for example, 2 1/2, five all over 2, you are given something like this. You know, this is an improper fraction, and this is one thing you got to really be mindful of. Partial fractions are only possible when the numerator is less than the denominator, or what the unknown you have in the numerator is less than the denominator. What you have at the top should be less than what you have at the bottom. So when you see a function wherein the unknown in the numerator is bigger than the unknown in the denominator, you cannot use partial fractions to decompose that fraction. It doesn't work. Like what you have here now is, this is an improper fraction. I'm just giving you an analogy what partial fractions look like. So this one now, you can break it down to say this is 2 1/2. You have this one here 1/2, but you have a 2 there. So this is still not enough. This can, and you know, this simply means 2 plus 1/2. So we are now decomposing this fraction. This is all what we are doing with partial fractions. You use techniques to do that. Where 5 over 2 becomes like 2 1/2. Now we know this is 2 plus 1/2. But these two, you have 1 there. It's still bigger than what you have at the bottom. The numerator is bigger than the denominator. So we still need to do something here with partial fractions. I'm just giving you an analogy for you to understand what partial fractions are. So this, you know, 2 can be written as 1/2 plus 1/2. This is 1/2 plus 1/2. This is 1 plus 1/2 plus another 1/2. When you sum up all this together, you get 2. Then plus this 1/2 we have here, plus this 1/2. So this now is all equal to 5 over 2. 1, 2, 3, 4, 5, 5 over 2. So because the denominator is now bigger than the numerator, so in partial fractions form, we have decomposed this fraction. So this is our aim with partial fractions. This is our aim, to make the numerator smaller than the denominator. Let's look at one example. Partial fraction. We have example, 3x plus 5, 3x plus 5, 3x plus 5 all over 2x squared minus 5x plus 3. 2x squared minus 5x plus 3. 2x squared. Correct. So we have this function here, and because what you have at the numerator here is x raised to the 1 here, x raised to the 1, and here your highest power is x raised to the 2. So it means this can be decomposed into fractions, into partial fractions, because this is smaller than what you have at the bottom. So now we are asked to decompose this function into partial fractions. In other words, what we have just done with 5 over 2, you have to break it down into smaller bits. Decomposition, that's what it means, break something down into smaller bits. So now, because we have a quadratic equation here, we can be able to factorize this function at the bottom. Yeah? We know what to do. We find two numbers, which when you add them together, you get minus 5. But when you multiply them together, you get plus 6. You're going to have 2 here, 3 here. So plus 6. So which two numbers, which when you add, you get minus 5. But when you multiply, you get plus 6. They both have to be negative. So we know that the factors of 6 is 2 and 3. So if you add 2 plus minus 2 minus 3, you get minus 5. But if you multiply minus 2 minus 3, you get plus 6. So it's minus 2 minus 3. These are our factors, yeah? We know how to do this. So what you have here, you have 2x squared minus 2x minus 3x plus 3. Broken down this. So now you have here 2x into x minus 2 minus 3 into x, 2x into x minus 1, sorry, x minus 1, yeah, and here 3 into x minus 1. So now you have 2x minus 3 into x minus 1. So these are your factors. So now this equation becomes 3x plus 5 all over. We have the factors of this. Let me start with the small one, x minus 1 and 2x minus 3. This is equivalent to saying 3x plus 5 all over x minus 1 plus 3x plus 5 all over 2x minus 3. So see what we have done? We have simplified this function here into this format. But with partial fractions, we have some methods we used. We are not going to solve it this way. I'm just giving an example. We'll stop here in this video. We have some methods we use, which we are going to explore in the next video. Thank you for watching. Bye bye.